Welcome back to calculus. Here we are, example 3, example C, trig substitution. We're going to do a couple long ones here. This will be a video, and we'll do a part 4 for our example D. So here's a problem. It may not look like trig substitution, but why is this not just a good regular old substitution candidate? Well, the issue we have, I'll just quickly address that, is if you let u be x squared minus 6x plus 5, then du would be 2x minus 6. And we don't have the minus 6. We don't have that, right? So we could handle that. We don't have the minus 6, so we could try to split this and do some kind of arc trig, and that would be possible. But I want to show this to you with the trig substitution. So this is going to be probably, either way is going to be long, but let's do it this way to get some practice with trig substitution. Okay, so first thing we need to do is make this look like what we want it to look like. It doesn't look like a trig substitution problem. We're looking usually for a square root. We got one of those, but then maybe something like x squared minus a squared. It's close to that, right? It's that, and then we have this whole thing. So what are we going to do? Well, what we can do, and really regardless of if we did the u substitution way with the arc trig, we would also need to do, we'd also need to complete the square. So either way, we got to complete the square. Let's do that first. So integral of x, and down here, what do I really wish was there instead of 5? I really wish it was a 9, right? In fact, you know what I'm going to do? I'm not gonna erase anything necessarily, but except this. But let's do this as an aside. Again, this is something that you can do off to the side and not make the meat of your problem overly long. I mean, it's already going to be really long. So let's do off the side. Let's complete the square on this. So I would really want a 9, right? So therefore, I have to subtract a 9. You see how I just added 9 and subtracted 9? Otherwise, it's the same. Well, this becomes that, and this becomes that, right? So I could rewrite this. I guess I will erase those. So we'll write this as x minus 3 quantity squared, and let's just call this 2 squared dx. So now it looks a bit more like what we were wanting, but I still want a u there. I don't want x minus 3, so we are going to need to do another substitution. So let's just do a simple let u be x minus 3, and then du would just be dx. And then this is Alfredo, as I call it with my students. So x is u plus 3. So you put that off the side. So we're going to need that. We're going to need that. We're going to need that. And we'll end up with the integral. Up top we have u plus 3. And down below we have the square root of u squared minus 2 squared du. Right, everything looks right. So our u is x minus, our x was u minus 3, or x minus 3 was u. Okay, looks good. So now this part under here looks just like we want for our trig substitution. So we will let u be 2 secant theta. Right? And then therefore our du is 2 secant. So secant shares with his buddy. Secant theta, tangent theta, d theta. We're going to need that. And we're going to need that. So I need to build the denominator. So first I need to square it. Then I need to subtract 2 squared. Let's just call it 4. Sure, let's call it 4 on both sides. And then remember what always happens here, every time. You're going to factor out, and the remaining part will condense. Secant squared minus 1 is tangent squared. You can look that up if you want. And then we have, so u squared minus 4 equals that. We square root both sides. And we're hoping to see some condensing. Yes, 2 tangent theta. Okay, so there we go. So when we plug back in, we have u is 2 secant theta. Let's put a plus 3 on there. Let's go ahead and put that in parentheses. I have a feeling that might be helpful. Oh yeah, because du is all this. So 2 secant theta, tangent theta, d theta. And then down below, it's just 2 tangent theta. Wow, that's nice. So we have lots of things that can cancel. 2's cancel. Tangent thetas cancel. And so we're left with, we can distribute this with the tangent, the secant theta. So we have 2 secant squared theta plus 3 secant theta d theta. Okay, take a little sigh of relief. That's good. We've done some good work here. But now we have some trig integrals. But we know what both of these are. The integral of secant squared theta. What is that? I'm just going to do this. This is not a necessary step, but just so we can, it might help you a little bit. Oops, oh, I forgot my d theta. Get rid of all that. Gotta have the d theta on the end. Plus 3 integral secant theta d theta. Okay, so we have 2 integrals. The first one is the easy one. You know this integral. And if you look back at my 8.3 handout, which I don't know if they've given that out to everybody yet, but my 8.3 handout, I talk about how you need to be immediately familiar with the six trig derivatives. And not just that, but the output of those. So when you see the outputs, so for example, we take the derivative of sine, you get cosine. Everybody knows that. Cosine, you get sine. Or cosine, you get negative sine. Yes, we all know that. Tangent transforms to secant squared. And you could write the rest of them down. You want to be familiar with this column over here. Whoa. This column, when you see it, you know you're good. So when I see a secant squared, I say, oh, we're good. This integral is just tangent theta. Nice. What's the integral of secant theta? That's a little trickier. It does involve a natural log. And it reminds me of the derivative in that it shares with this buddy, but now it's in a plus relationship within the absolute value of that's being natural logged. Now you can box that, right? No, because it's in theta. I don't want an integral in theta. I substituted to theta to help me do the integral, but I need to go back. So what's our relationship with theta in another variable? Here we go. Here's a relationship with theta to u. U is 2 secant theta. So let's write that down. I'm going to kind of get rid of some of this. Okay. So I already forgot what I just said. U is 2 secant theta. So secant theta is u over 2, right? So, because I'm going to need, oh, there's that. I could plug in u over 2 there, but I need tangent theta in a couple places. So I'm going to draw my triangle, call that theta. So secant is a reciprocal of cosine, so it is hypotenuse over adjacent. So you could check me on this, but I'll just tell you this is going to be u squared minus 4. So tangent of theta is going to be square root of u squared minus 4 over 2. I'm going to need that. Okay. So I am really running out of space here, but we'll do our best. 2 times this thing, u squared minus 4 over 2. Hey, the 2's will cancel. It's nice. Plus 3 times the natural log of the absolute value secant theta is just u over 2 plus square root of u squared minus 4 over 2. Hey, common denominator. Didn't have enough room. Okay. We have that. Then we can, this part just becomes square root of u squared minus 4. I can combine these as u plus square root of u squared minus 4 over 2 plus c. And maybe you think you're done, but we could do a little bit more. We can, you know, if you have a natural log of a ratio, you can break that up, right? So this guy is just waiting on us. So I can break this up as 3, and this is going to be all of this, 3 times the natural log of the numerator minus natural log of the denominator, which 2 is always positive, of course. 2 is a positive number, plus c. Now, I'm going to move down a lot here. If I distribute that 3, have that minus 3 ln of 2 plus c. Now, what is that equal to? That's just equal to some other constant. We'll just call it d. And then it looks like we're done, right? Except, what was our original problem in? If we can go all the way back up, it was in x's, not u's. So I need to go back to the x world. What's our relationship between x and u? It is a nice one. U is x minus 3. Let's write that down here. U equals x minus 3. Okay. So I actually have to do this, believe it or not. Plug in, and so this becomes x minus 3 quantity squared minus 4 plus 3 ln of x minus 3 plus square root x minus 3 quantity squared minus 4 plus the constant we're now calling d. And this is it right here. This becomes what, x squared minus 6x plus 9, or x squared minus 6x plus 5. Hey, that looks familiar. Look back at the beginning. Plus 3 natural log absolute value of x minus 3 plus the square root of, hey, this is the same computation we did over here. So it's x squared minus 6x plus 5 plus d. That's as good as it gets. So how do we know we're done? Well, we went from thetas to u's to x's. X was the original problem, and you're often going to see when you get back to the end, it looks similar. Like we had these square root of x squared minus 6x plus 5's in it. And that's a long haul, but lots of things we worked on. I do want to make one other comment. I meant to say it in the middle of this problem, but there's a problem on the homework, and it's pretty common, where right here, this was in my building step, as I call it. Instead of saying they want a square root, they say they want a 3/2 power. What if that happened? If you wanted the 3/2 power, what I do, say you knew that this was true and you wanted the 3/2 power, for example, I would square root it first. Let's just do this. I'd 1/2 power at first, which is the square root, and then I'd cube it. And that would be 8 tangent cubed theta. So as you get to that one, 3/2 powers are no problem. I'd square root it first. It's going to simplify nicely in the square root and then cube.